Good evening, everybody. I'm Beryadi. I'm here as moderator for this event. Welcome, Miss Bonsoir Golamo. Comment ça va? Je m'appelle Ferry. So I will be a moderator in this event. I will speak with English because I know I cannot speak French properly. So therefore, before we start our discussion, I will start to give a brief of your CV, what we got here. Wait a minute. So, wait a minute, it's still working. All right. So, Mr. Guillermo Lorilleux, correct me if I'm wrong with your pronunciation. He got a lot of experience as a seasonal geologist with range exploration, mineral resources for a lot of commodities like uranium, nickel, copper, gold across Canada, Mongolia, Australia, Africa, South America, and so on. It's a lot of experience here. We are lucky to get him as a speaker today, and also with the educational background from the École Nationale Supérieure Geology, Geology Engineering from France, and doctorate geoscience from Politics de Laurent, Francais, and he is now working as a general manager Mineral Resources Group at PT Merdeka Mining Services. From 1997, he's working as a exploration geologist in Canada and mission in Africa 2002 to 2004, and project geologist in Mongolia, Australia, North and South America, Central Africa, and Far East from Arefa and now Orano. And from 2013 to 2022, he was principal resource geologist and a resource and reserve manager for Eramet in New Caledonia. And now he's a general manager, Mineral Resources Group of Indonesia. Today, Mr. Guillermo will discuss about the resource estimation because he is a practice in this particular subject. We are happy to have you here, Mr. And you can start your presentation, and after this, we will have a Q&A. Anyway, here we go. Thank you.
Terima kasih banyak, Pak Feryadi. I hope my Bahasa is okay. Your French was quite good, actually. No problem.
Merci beaucoup.
Merci, merci. Okay, I will share my screen. Go to slide mode. Yes. Can you see my slideshow correctly?
Yes, it's clear.
Perfect. I will start then.
All right.
Thank you for the introduction. So this webinar is a sharing knowledge session on the specificities of mineral resource estimation of nickel laterite. It follows last week's session related to the geology and metallurgy of nickel laterite deposits. So there will be a few references, obviously, to what we discussed last week. So mineral resource estimation methods and parameters are dependent on nickel laterite characteristics and the type of nickel laterite deposit, as we've seen last week. I will present here some of the specificities of mineral resource estimation, covering the classical steps of resource estimation from resource domaining to resource classification, as presented on this slide. So let's start with resource domaining. The lateritic profile is associated with vertical variations of grades and bulk density in relation with chemical and mechanical processes, as presented last week. Consequently, to improve stationarity of estimation variables, it is essential to separate the bedrock, the saprolite, and the limonite for resource estimation, leading to a stratigraphic domaining approach. As you can see here on this schematic section, with basically these lines would represent basically domains boundaries between bedrock, saprolite, and limonite. However, within limonite and saprolite, the grade and density still vary a lot, as shown by vertical nickel, magnesium, and iron Swass plots in saprolite at Thiebaghi. So this is from a paper from Olivier Bertoli in 2014. Therefore, a refined domaining approach may be required based on geological and geochemical variations. The saprock can be separated from earthy saprolite, and so this is this dashed line here, and the yellow limonite can be separated from the red limonite. In some deposits, the transition between yellow and red limonite corresponds to a sudden change in nickel grade. Geochemical criteria are commonly used to help determine boundaries between domains. This is especially true for the limonite-saprolite boundary, which is generally difficult to pick visually, as it is very progressive. And the transition zone is also sometimes domained out. In addition, specific grade domains may also be relevant if sharp grade gradients are identified in cross-sections. The boundaries of these domains will generally be defined as hard during the estimation process, but a contact analysis is required to confirm the relevance of the domain boundaries and how they need to be treated during the estimation process. Even with a refined domaining approach, the continuous nature of the vertical grade and density variations implies that vertical stationarity can never be perfectly achieved. Consequently, search ellipsoids used for estimation are generally very flat to ensure local stationarity.
Sorry, Pak Guillaume, I think I'm sorry to interrupt ya. For the display setting ya, I think you need to switch the display setting because we only see the small.
Yeah, can you make it bigger? Because this is just a small thing. Because more.
Okay. That's what I was asking, if you could see correctly the slide. So it's reversed.
Okay, sorry about it.
I will stop sharing. So you can see the text and okay. So yes. I will try something different then. Last week worked very well, but this time looks like not. So I will try something different. Okay, I share my screen again. Okay, let's try this one. Yeah, okay, let's do a test. Sorry about this disruption.
All right, so. Okay, you can go with this presentation.
Okay, now you see my screen now?
Yes, okay, all right.
So I will go in slideshow.
Yes, all right. Okay, everybody's happy with it? Hello?
Yeah, it's good.
It's okay for you? It's
Yeah.
okay for everybody? I think yes.
All right.
All right, you can continue, sir.
All right. Just let me know if I need to come back later to the first slide. Maybe something was not clear. Okay. So stratigraphic models can be generated by interpolation of surfaces based on intervals defined in drill holes. Inverse distance and ordinary kriging will generate smoothed surface unless the drill hole spacing is tight enough to reflect the spatial variability at the SMU scale. Ground penetrating radar, GPR, and electrical resistivity tomography, ERT, data can be used to better model the spatial variability between drill holes. GPR has been used to successfully define regolith interface at Konawe in Indonesia, as shown on the figure on the left. And I will go back to my laser. This figure here, especially the limonite-saprolite boundary. Boundary wireframes can be generated based on several survey lines and used for resource domains. ERT, ground or airborne, has been used to help define the bedrock regolith interface and some of the main structures as shown on the figure on the right. This is in New Caledonia. And both methods necessitate the use of drill hole data to calibrate the interpretation. Each deposit has a unique response, which may vary within an ore body. So calibration on one deposit cannot be used on another one. Notably, ERT data depends on the abundance and salinity of the groundwater, which varies from one area to another. Interpolation by inverse distance or kriging are commonly used, as I just said, and is appropriate for global estimates. So this is the upper part of this figure. We can see like smoothed surface generated by kriging. But conditional simulations can also be used to generate the regolith layers with a better reproduction of the spatial variability between drill holes, as shown on this figure here. As you can see, it's a lot more realistic for those who actually work on nickel laterite deposits. So these conditional simulations, will overall give a similar volume, but locally will give a better representation of the variability especially in the saprolite. From the basin to the slope deposit types, referring to last week's classification that was presented, the structural complexity increases, and this may lead to changes in the regolith sequence like local profile inversions and repetitions. Therefore, the generally acceptable stratigraphic modeling approach for basin-style deposits may not be appropriate for plateau or slope deposits. But in all deposit styles, the development of karstic systems that we described in the previous presentation may be responsible for disruptions of the sequence, notably in the vicinity of dolines or resorption cells, where regolith contacts can become very steep, sometimes faulted, and locally vertical. Significant amount of material trapped inside another domain with a different weathering degree may also happen. In such cases, a stratigraphic modeling approach may not be appropriate even for basin-style deposits, depending on the spatial precision required. That is global versus local estimate. So more complex, non-stratigraphic models can be achieved by modeling solids based on classical section-by-section explicit modeling approaches, but this can be very time-consuming. This section is an example of development of preferential weathering in oblique fracture systems, which may lead to nickel-rich saprolite mineralization below bedrock, like in this area or this area. Pre-Gaussian simulations can also be used with the advantage of being able to map the uncertainty in the volumes and providing the proportion of each facies in each block. The method is also less time-consuming than classical manual modeling once simulation routines are set up, obviously. These figures correspond to results of pre-Gaussian simulations implemented by FEBV in 2019 in Kwawa in New Caledonia. From 100 simulations, the standard deviation of the proportions inside each block was calculated as displayed on the right figure. The low uncertainties on the facies proportion corresponds to the low standard deviation located in the well-drilled areas or in the areas where the facies are continuous from one drill hole to the next. Implicit modeling may also be used, but may require specific constraints to be able to provide realistic results. Implicit modeling may not be appropriate if drill hole spacing is too wide. One advantage of implicit modeling is that it allows to update rapidly a model after addition of drill holes. Multiple point statistics can also be used in the case of deposits already being mined, based on 3D model training images from the reconciliation model. It allows generating 3D numerical models in accordance with the training image. And lastly, not least, machine learning algorithms are now commonly provided by commercial software and or through coding libraries that can be used to directly generate model boundaries from data, even without any geostatistical input or constraints. Such models need to be assessed with care and validated by comparison with a more classical approach. Machine learning models generated using tightly spaced data are likely to give good results. So the increase of structural complexity from basin to slope deposits may also require defining several geographical domains controlled by faults and breccias as they may act as fluid barriers and lead to unequal spatial grade distributions. More generally, in all deposit styles, variations in bedrock composition may be responsible for lateral grade variations. For example, zones of bedrock corresponding to laterite or areas rich in feldspathic dikes may be responsible for higher aluminum grades in saprolite and limonite compared to harzbogitic bedrock. Spatial changes of hydrological gradients may also generate lateral grade variations. And large deposits may also encompass several types of geomorphology, which may require different domains. The relevance of geographical domaining depends on the type of transition. A domain boundary may not be appropriate for a very progressive grade change. The determination of geographical domains can be performed manually based on structural interpretation and the modeling of structures. In order to model geochemical variations for several elements to be estimated, clustering methods like K-mean may also be used to define sample groups and help define geographical domains if relevant. This is a conceptual example of manual domaining of low and high aluminum zones in limonite based on the combination of geochemistry and structural interpretation. The geochemistry is visualized by using cockade maps where grades are represented by color and thickness represented by the size of the disks. The combination of vertical domaining with such a geographical domaining can lead to complex domains. To avoid unnecessary complexity, it is essential to have an integrated approach based on the geological understanding of the geochemical variations. Like in this example here, the aluminum grade variations are likely related to these structural controls. As part of the exploratory data analysis, descriptive statistics, notably the coefficient of variation, histograms, log probability plots, and vertical swath plots may be used to assess the relevance of the domains and the variable stationarity. So the domaining exercise may require several iterations using validation as a feedback loop for optimal results. Contact analysis allows to assess the relevance of the domain contacts and the type of resource boundaries to be used, hard, soft, or semi-soft. I will now go through some of the key features of exploratory data analysis for nickel laterite. Several elements need to be estimated, considering not only elements of economic interest like nickel and cobalt, but also elements that may have an impact on the metallurgical process. Pyrometallurgy constrains the ore chemistry, more specifically iron, basicity, that is the magnesium on silica ratio, and aluminium, whereas the hydrometallurgy process requires specific magnesium and aluminium grade ranges. The carbon content may also be required as it is deleterious for hydrometallurgy. Constraints in iron grades vary significantly between low reduction and high reduction pyrometallurgy as well. The bulk density values can be determined based on a combination of lithology, weathering degree, and degree of serpentinization. Such relationships can be established based on sufficiently representative number of samples. Another approach to define bulk density is to model the density by establishing regression models between geochemical elements representative of the vertical regolith profile evolution and the density, like this diagram here showing the dry density against iron, thus reproducing the natural vertical bulk density variations. These two approaches allow populating the density in the entire dataset. And furthermore, depending on ore processing, estimating granulometric fractions may also be required in some cases. Now we just took a slide on the constraints of additivity. The grade is the amount of metal per unit of dry mass. Therefore, grades can theoretically only be interpolated if the densities and sample lengths are constant for additivity reasons. However, in nickel laterite, the density variations can be quite extreme with the same unit. Therefore, the grade is not additive, as for given grade and sample lengths, the amount of metal will depend on the density of the sample. So in this example, there are two samples of soft and hard saprolite with different grades, density, and length. If we calculate the arithmetic mean to define the grade, it will be wrong because of density and length variations. It is therefore required to weight the grade by length and density to define the mean grade. Accumulation and partial density can also be used instead of weighted grade, where accumulation is grade multiplied by partial density, and partial density is density multiplied by length or length proportion. Co-kriging of accumulation and partial density is fundamental to respect the correlation between accumulation and partial density. Otherwise, the recalculated grade, the recalculated grade by dividing the accumulation by the partial density can locally be strongly biased. The impact of using grades not weighted by density can be reduced by using a flat search ellipsoid, as well as separating hard and soft saprolite in the estimation, for example, by using an indicator kriging approach. In this case, it can be acceptable, but not theoretically correct, to estimate grades directly, provided that there are no significant correlation between grade and density. And this is not always the case. Indeed, the nickel laterite formation processes implies density variations, which are directly linked with the leaching of silica and magnesium. So in general, iron is strongly anti-correlated with dry density and magnesium. And magnesium is strongly correlated with density in saprolite. Nickel can be strongly anti-correlated with density in rocky saprolite as well. Consequently, the use of non-weighted grades must be done with a lot of care, and validated, ideally validated by comparison with accumulations or weighted grades to ensure the impact on the estimation results is not significant. In order to take into account relationships between correlated elements, best practice is to use a multivariate methodology for the estimation by co-kriging or co-simulations. An intermediate approach is to define groups of variables based on correlations, using, for example, a 0.7 correlation threshold to define variograms using a representative element within the group. Correlations can be assessed using a Pearson correlation coefficient matrix, like shown on this figure, or a principal component analysis. It is necessary to visualize the correlation diagrams between pairs of elements to understand the nature of the correlation and the eventual existence of several populations. It's also a way to get an assessment of the estimation domains. Medium to strong anti-correlations or correlations between bulk density and iron, aluminum, magnesium, and silica can be used to model the bulk density as mentioned earlier. Slide. Yeah. The top capping of nickel may be required to improve variograms in case of extreme, top capping of nickel or cobalt may be required to improve variograms in case of extreme nickel or cobalt values and to avoid spreading locally high-grade intersections. Bottom capping is sometimes used for deleterious elements. For example, iron for saprolite to be processed by pyrometallurgy. But one must be aware of the potential impact on stoichiometric closure. So, because the stoichiometric closure will be impacted negatively by this bottom capping. Normal score variograms is advised for skewed distribution. This is like not specifically for nickel laterite, but this often the distributions are often skewed for silica or magnesium and iron. And in order to improve the modeling of the horizontal continuity, unfolding is generally used based on the limonite, commonly used based on the limonite-saprolite interface. The estimation is then performed in the unfolded space, or a dynamic interpolation can also be used. Nickel in limonite is typically more continuous than in saprolite. The horizontal nickel continuity is exemplified by these diagrams from Goro. You can see here that the nugget effect in the earthy saprolite on the right is a lot higher than in the limonite on the left. And the range in the earthy saprolite is less than in the limonite. Major elements like silica, magnesium, and iron also tend to present a better continuity in limonite than saprolite. Now we'll focus a little bit on saprolite, on the fact that it's a two to three phase domain. So depending on the degree of weathering, serpentinization, fracturing, and the nature of the bedrock, the saprolite may consist of two phases, earthy or soft, and hard. The hard peridotite can be fresh, fully weathered and mineralized, or only weathered in the periphery with nickel grade decreasing inwards. So this has been also described last week in the saprolite, different types of saprolite depending on degree of serpentinization. Both fresh and weathered hard saprolite can coexist. The hard and soft phases generally have different grades and densities. So this histogram here is an example of statistical distribution of dry density composites in saprock, clearly showing two populations related to weathered and fresh peridotite. In terms of geological logging and sampling, These saprolite phases should not be mixed unless bulk mining of saprolite is performed and no screening is used. Some degree of mixing cannot be avoided to account for mining dilution and ore processing where relevant, for example, screening, and to allow also for enough sampling material. In the case of metric interval logging, each interval may have a fresh sample and a weathered sample, knowing that weathered can also be broken down into soft and hard. So there are two composites for each interval in that case, and the mixing is limited to the dilution of small, fresh intervals in weathered material, which is done as a function of mining selectivity and ore processing. This data can actually be used to define indicator domains to estimate fresh and weathered samples separately. In the case of geological interval logging, compositing may mix both phases to some extent. This may reflect mining dilution, but may not be appropriate in the case of screening. In this case, indicator domains will therefore be based on mixed population, so they will be not optimal. Within the saprolite domain, an indicator kriging approach can be used, as I mentioned in the previous slide, to specially define hard and soft domains and interpolate variables within them. Pre-regression simulations can also be used to specially model the different phases. This is an example from Kwawa in New Caledonia, where the fresh rock, the coarse saprolite, and the muddy saprolite are separated. Now going to the resource estimation methodologies. The most common estimation methodology used in nickel laterite is ordinary kriging. This is generally acceptable for large deposits with a low cutoff grade and low selectivity constraints, like for some basin-style deposits. To address the lack of stationarity, apart from the flat search ellipsoid mentioned above, earlier, universal kriging using the drift of the given variable as a residual can also be used. Another approach is to use intrinsic random function of order k, IRFK, as described as short. And from basin to plateau and then slope deposits, the cutoff grade will tend to increase. And depending on the proportion of sap rock and the stripping ratio, as well as the mining selectivity. Ordinary kriging is not well adapted to the application of a high cutoff grade due to the smoothing effect of the kriging, which may generate a biased estimate. In this case, nonlinear estimation approach will be more relevant to estimate recoverable resources at the SMU scale. More specifically, conditional simulations or uniform conditioning can be used to better define the resource at cutoff. In this example, the grade tonnage curves for an iron ore deposit reflect the difference at cutoff between ordinary kriging in red and simulations here. With, if you apply a high cutoff, much more tons at high cutoff using simulations compared to ordinary kriging. Both conditional simulations and uniform conditioning require sufficient closed space data in order to define the histogram and the variograms at the SMU scale. Pardon me. Conditional simulations take into account both support and information effects and allow performing the risk analysis by calculating the uncertainty associated with the estimation at the SMU scale. If the resource domains were defined based on simulated facies domains, conditional simulations can be used to generate grades conditioned to the generated facies domains and chemical analysis. And uniform conditioning is applicable if the grade distribution is diffusive in order to apply the discrete Gaussian model for change of support. Now, just one slide on the validation of resource estimation. The resource estimation validation criteria include the statistical validation, which is general for all types, I would say, of estimation, the SWAS plots, and the visual validation on vertical cross-sections and horizontal plans, and better using the unfolded space in that case. But there are also specific validation criteria for nickel laterite estimation, which include verifying that the sum of oxides of estimated blocks does not deviate too much from the stoichiometric closure as defined on the composites. Also ensuring that the grade cross correlations are similar between estimated blocks and composites, and ensuring the consistency between estimated dry density, wet density, and moisture content and their coherence in comparison to values in composites. And if there are any issues regarding these verifications, they should concern a minor amount of blocks and require some post-processing to get a final block model. In order to ensure the respect of the total sum of elements, a log ratio approach, additive log ratio transformation combined with normal score transformed and minimum maximum autocorrelation factors has been proposed by Mueller in 2014. We now go through the resource classification. You can see on this vertical cross-section that the continuity of the thickness is much better in limonite than in saprolite, due to variations of elevations of the bedrock in relation with its structuration and mainly the location of fault or structures. In nickel laterite deposits, the geological continuity is generally much more critical than the grade continuity. Therefore, in nickel laterite deposits, it's fundamental to consider thickness variations and not only grades to assess the degree and confidence on the geological continuity for the mineral resource. In 2014, Parker and Dom presented a review of best practice in mineral resource classification and mentioned in some deposits, thickness is more uncertain than grade and should govern the classification. Example of nickel laterite saprolite deposits. A DHSA typically must use the thickness variations in limonite and saprolite. In the lower part of the saprolite, the sharp grade and density contrast between weathered peridotite and relatively unaltered bedrock is responsible for a very poor geological and grade continuity as shown on the schematic section. The continuity improves in the upper part of the saprolite as there are less and less remnants of unaltered peridotite and the weathering is more intense. And in the yellow limonite, the continuity improves even more as the material is more homogeneous and the mineralization is more diffusive. In some cases, lateral nickel grade variations in limonite reflect ghosts of garnierite veins not fully digested by weathering, as shown on this schematic profile from Bailly, 2014. Magnesium and silica grades in limonite may also be impacted by this phenomenon. These variations are less pronounced than in saprolite. These variations are more likely in plateau deposit types that underwent advanced saprolite development than in basin deposit types. The horizontal nickel continuity is exemplified by diagram from Goro. So this is actually the slide we already saw before. The nugget effect in the earthy saprolite is a lot higher than in the limonite, and the range in earthy saprolite is less than in limonite. Therefore, considering the thickness, the grade, and the density variations, the geological and geochemical continuity increases upward with a strong contrast between saprolite and limonite. For a given drill spacing and a given production rate, considering a probabilities approach of classification, The resource classification in limonite is expected to be higher than in saprolite. We've seen that the degree of confidence on the geochemical continuity in limonite and saprolite is different for a given drill hole spacing. This means that we may need different drill hole spacings in limonite and saprolite to get a consistent resource classification. This is difficult in practice, even though not impossible if the number of mining areas allows a rotation between limonite mining, saprolite drilling, and saprolite mining. But this supposes a very good coordination between drilling teams and mining teams and a combined drilling mining planning. However, this is not optimal for business mine planning as saprolite is not well known in advance. For example, we can get inferred saprolite while limonite above is indicated, and saprolite will only get indicated later after the limonite has been mined. So the other option is to stay conservative, but that leads to over-drilling limonite. And in this case, drilling cost optimization is required. So geophysics like ERT data can be used to try to identify areas of less variability in saprolite and therefore reduce drill spacing requirements on those areas. But a cost-benefit analysis is required to ensure the cost of ERT survey is less than the drilling cost reduction. Another way is to replace diamond drilling by RC drilling. This has been done successfully in New Caledonia and in Colombia, for example. But if we take the Indonesian context, RC may not be always cheaper than diamond drilling. And there are also potential rig moving issues in soft material to take into account. And using RC also requires rig adaptation and tests. So it's you cannot use straight away a classic, let's say, RC rig that you can use in a gold mine. And RC drilling does not work well in poorly serpentinized environment due to sample contamination, especially in areas of alternation between hard and soft materials. So the resource classification by the competent person is not necessarily an easy task, and it cannot be done in isolation and require proactive communication with exploration and mining parties to understand the risks and to optimize costs, taking into account all available information. In addition, the grade continuity is not only related to elements of economic interest, like nickel and cobalt, but also to elements which are critical for the metallurgical process. That is iron, magnesium, silica, and aluminium. In some cases, some of these elements are significantly less continuous than nickel. So as a best practice, and leaving aside thickness, the less continuous element should govern the classification. This is supported by a quote from the 2020 CIM guidance on commodity pricing and other issues related to mineral resource and mineral reserve estimation and reporting. So the quote is the following: as it is not acceptable to report different confidence categories for those individual commodities or metals, the lowest classification should be used where a byproduct, co-product, or deleterious element has significant influence on overall economics or economic outcomes. The degree of serpentinization may have an influence on the geological continuity as well. We have seen before actually in saprolite. Highly serpentinized saprolite is generally more continuous than saprolite with a low degree of serpentinization. The mineral resource classification also depends on the cutoff grade, as the application of a low cutoff will generate more continuity than a high cutoff. The geological continuity also depending on the type of deposit. In addition to drill hole data quality, the quality and precision of the topography is important to consider, especially for basin deposits, where the surface is a major component of the deposit dimensions. And different classification between limonite and saprolite may lead to difficulties in terms of mine planning. If not possible, the most conservative classification should be retained, referring to the previous slide. So to conclude, different deposits and ore types may require different resource domaining and estimation methods and parameters as a function of geological and grade continuity and cutoff grade. From basin to slope deposits, as the structural complexity and nickel grade increase, the geological modeling may evolve from stratigraphic to more complex 3D domaining, and the resource estimation may evolve from ordinary kriging or co-kriging to nonlinear methods like conditional simulations to avoid bias estimates at cutoff. It is essential to take into account additivity constraints due to variable density. Multivariate estimation is best practice to ensure better local estimation and respect correlation between variables, especially between accumulation and partial density, as well as a stoichiometric closure. The coexistence of two phases intermingled in saprolite may require specific approaches like indicator kriging and are strongly dependent on how the geological logging and sampling is performed and what is the level of mining dilution and type of ore processing. Limonite is generally much more continuous than saprolite, both geologically and geochemically, which impacts resource classification. The competent person has a key role to communicate risks and proactively communicate with exploration, reserve, and mining teams to optimize costs, taking into account all available information. And that's all for this part. And thank you for your attention.
Okay, thank you very much. Merci beaucoup. All right, I would like to summarize before we go for the Q&A. Just give me less than 5 minutes to summarize what has been presenting today. We're gonna start with this, like Mr. Guillaume said, this is the sharing knowledge. She started with the mineral exploration. He discussed a lot about the mining, and this is discussed also about the stratigraphic and non-stratigraphic. And he also introduced about the pluri-Gaussian, multi-point statistic and so on, and discussed quite a bit about the machine learning. It's quite interesting today. And also he discussed also the gravically constraints, and every single place they must have a different domaining, like plateau, basin, and so on. And also he suggested to do the domaining validation. There is the hard and soft boundary, and we can go also with the statistics, something like that, and we go with the ones or several points. And also we can do, don't forget about the exploration data analysis. Is quite important today for economic elements, pyrometallurgy, for example. We know about the basicity, and hydrometallurgy. We deal with the magnesium and aluminum, and also bulk and measure for density. And if it is important, we can go with the granulometric. And remember, don't go with the arithmetic mean for the grade. We must go with the weighted mean grade, and so on. And all right, also the caving, improve the variogram, and also normal score if we have a skewed distribution, for example. And the last definitely before least, so to make it quick, resource classification, and also the validation. Yeah, we have the visual investigation statistic and stoichiometry correlation between the element dry and wet. This is the new for me, to be honest. Dry and versus wet for the mineral. And definitely last but not least, although computer is important here, but we must understand how to go with the classification, thickness, and so on, what already discussed by Guillaume. Thank you very much. And we are now open for the Q&A. Just raise your hand here and you can ask directly to the Mr. Guillaume. And I now open for the 3 person for the first session. All right, you're gonna start now. Any questions so far? Okay, if not, I will start with my question. Any question from the audience? Oh yeah, this is Hari Irwanto. Okay, you can go now with your question.
Okay, thank you for the great presentation, Mr. Guillaume. My name is Hari Irwanto from PT Prima Berjaya. And from your presentation, there are 2 methods for continuity analysis and of course resource estimations, which are unfolding and dynamic anisotropy. And from your experience for nickel laterite deposit, which one is better, and the pros and cons of each method? Thank you.
Okay, thank you for this question. So my experience is mainly using actually flattening unfolding, not much using dynamic interpolation. But I would expect the result to be very, very similar. And I guess, yeah, if one is to use, I mean, it would be ideal for an estimation probably to compare both methodologies, but it's hard for me to say which one is actually better. I think dynamic interpolation, if the algorithm is well designed, there is no reason why it would not work. But maybe someone else in the participants have some experience to share actually, because this is really open discussion, yes?
Okay. All right, Hari. Does it answer your question as well? Are you happy with it?
Okay, thank you.
All right.
Guillaume. I think
right.
that's answer my question already. Thank you.
All right.
Thank you. Sorry,
Perfect.
I can't do much more than this.
All right, anyone else with your question? Please raise your hands and you can switch on your audio and you can ask with Mr. Guillaume. Anyone? If not, I will ask. Wait a minute. Okay. Now, I have a question. Basically, competent person may deal with this with the resource classification, for example, based on the Cardidec-Delen's journal. I think 2022. He said there is three way to do the resource classification based on the geometrical approach, based on the geostatistical approach, and last one, but it's quite, I think it's not really popular now, but we are starting to understand about this. The last one is machine learning. Now, in your experience, because I look at, you have a lot of experience in nickel laterite worldwide, not only Indonesia, but in Koniambo, Goro-Goro, and so on. What do you think the best for us, because it's quite subjective sometimes, to classify the resource properly?
Yeah. Yeah, so look, what I really, in my experience, it's, I repeat myself a little bit here. It's, there are a few key points. One key points, and that's why I insist so much, is that I've seen classification applied equally to limonite and saprolite. And that can happen, but that needs to be demonstrated. But in my experience, most of the time, the continuity in limonite is clearly significantly better than saprolite. So obviously that makes things a bit more difficult, as I explained, because yeah, it's more difficult to manage to have two different classifications, but this is a reality that we cannot deny. In terms of method, so using the thickness is really important, because the key point, I guess, is, and it all depends, of course, of what is the target, what we want to produce. If it's a deposit which is mainly focused on limonite with extremely minor saprolite, maybe it's not such a big deal because it's very, very insignificant in the resource. But if we have a significant portion of saprolite and limonite, we have to take this into account. And the saprolite variation, the thickness variations in saprolite are very important to consider in the criteria for classification. I think one of the best approach is what I always call the Parker's law. So to take into account the volume of production given a production rate per year or for 3 months for measured, let's say, and for 1 year for indicated, assuming variations of plus or minus 15% with a probability of 90%. I mean, this I think most of the people working in the resource estimation space know this now. This is, I think, best practice now, and that can really help actually if you have a mine with a significant production volumes, production rates. That can help to decrease the requirements for drilling. So that needs to be taken into account in addition of the actual continuity. So it's kind of a complex exercise, in fact, because you need to take into account, it's a multi-criteria approach where we need to take into account the quality of the data, the degree of confidence on the geological model, the quality of estimation, and the differential continuities between two domains. Yeah, so that would be my recommendations, basically. And each deposit is different, obviously, but there are trends that we can find everywhere. And the multivariate aspect is also very important. But as we know, as I said, we classify very often using the nickel, but sometimes, I mean, it's not sometimes, I mean, the other elements are as important. I remember talking to metallurgists in my previous company in New Caledonia. And it was concerning saprolite ore for a pyrometallurgical plant. And people were more concerned about the iron content and less concerned about the nickel, because they know the nickel is always there. Sometimes it's less than expected and it's not good, but if the iron is too high, they know potentially it can break the furnace. The RKAF can just be seriously damaged. And this is actually more critical for them. So that means the geologist, the resource geologist, needs to put as much attention on nickel as on iron, or sorry, I should say the reverse way, on iron as nickel, as an example. So yeah, so that puts sometimes a competent person in a difficult situation, because looking for nickel, sometimes nickel is more continuous, and we end up looking at iron or aluminium or magnesium, and we found that it's less continuous. And that actually impacts the overall classification, because we cannot have a separate classification for each element. That's one thing.
All right.
Yeah.
All right, perfect. Thank you. Anyone else? Now is a good time for you to ask with the expert. If you have any question about the domaining, how to make a geological modeling and so on, please raise your hand. Because this very interesting topic. Anyone? Okay.
Yes, Pak.
Okay, please.
Thank you for the presentation, Pak. It is a good presentation. I'm Agus from PT Geoservices as geologist. My question is, what are the key factors that influence the accuracy of mineral resource estimate in nickel laterite deposit? And how do geologists account for variability in laterite profile?
All right.
That's my question.
Okay, thank you. All right, Mr. Guillaume, you can answer the question.
Okay.
All right,
Great
go.
question. Very good.
Yes.
So the first one, so key factors affecting the accuracy of the resource estimations. I would say that would be probably a similar response for all estimations. Obviously, I would start with the jury spacing. Basically, we need to have that's a, as you know, that's the main thing that will impact your estimation accuracy, which can be reflected by your slope of regression of let's say nickel. If you look at nickel elements, and if you have areas of close jury spacing, that's where you're going to get good accuracy. If you have a really wide spacing, you have less accuracy depending on your diagrams. So this basically, of course, in a nickel, because it's a multivariate approach, we have to consider the accuracy of all the elements, what I was mentioning before. So that's where it can get a bit more complex, including density, because to me the best practice is really to populate the density in everywhere, using either a regression law or a correspondence between density and the geological characteristics like lithology, degree of weathering, or degree of suboptimization. And your second question, sorry, was about, I forgot about it. Sorry, could you please repeat your second question?
Hello, Agus, can you repeat your second question?
My second question, how do geologists account for variability in laterite profile? Bagaimana ahli geologi memperhitungkan variabilitas dalam profil laterite itu?
Do you get it?
Yeah, it's quite a general question, yes.
Yeah.
Are you talking about like, okay, so because we have both vertical and lateral variability. So the geologist, so I guess the resource geologist, I guess in the question. So this is referring, for me, the first thing is to look at, is it possible to, so during the first part of the estimation, it's one of the first part is really the domaining approach. If there is a variability of the grades, the idea is to see if this variability, at what scale is the variability actually. So we know at a small scale there is always some variability. At a larger scale, are we stationary in? Do we have stationarity in our domain? So if we take the entire, let's say the entire deposit, do we have like horizontal stationarity or not within each layer? If not, is it possible to define some domains? Do we have some specific geological controls? I think we need to look at all ways to understand the geology and going through mapping, through using geophysics or already available drilling data, how the thickness, the variations, what are the geochemical variations. There are many ways we can combine all this information to try to define areas of better continuity, better stationarity. Sorry. Yeah, I think that's how I would approach this question, and same in the vertical direction. That's what I was describing in one of the first slides. It's really to look at, we know we have a lack of stationarity and we know we have this variability. So we try to define, we try and define domains based on the geological variations, geological and geochemical variations, and also to use some, for example, relatively flat search ellipsoids when you do the interpolation, so that we have a limited variability within our estimation ellipsoid, because we know already it's going to be varying a lot in a particular direction. And also by domaining separately in the saprolite, we know there is more variability in the saprolite, especially the rocky saprolite, because we can have a combination of borders of fresh rock. Sometimes we have a border of weathered peridotite but still hard. All this in the middle of soft saprolite. So that makes things a bit difficult in terms of it's extremely variable. So there are ways to either by doing indicator kriging or regression simulations, what I was mentioning before, to try to isolate, to separate these domains, so that we can work within these domains to do the estimation. I don't know if this is the sense of your question, or.
What about you, Agus? But are you happy with this? Does it answer your question?
Thanks for your answer and your explanation.
All right, cool. We still have the last question from the audience. Okay, this is, I think there is the two. All right. Who is the first? Just start your question.
Okay. Thank you very much, Pak Gil, for your insightful presentation. I have some question. My name is Tommy Hidayat Herawan. I'm from Akita University. I want to ask about, in case of domaining in nickel laterite deposit, is it necessary to add metallurgical behavior, considering the its metallurgical behavior? In nickel laterite deposit, is it more controlled by geochemistry, such as nickel content, iron, or magnesium, or is it more controlled by physical properties, like, or lithological properties? For instance, like red limonite, yellow limonite, saprolite, in case of metallurgical behavior. So there's two questions. First question is it necessary to add to consider metallurgical behavior in terms of domaining? The second question is, in laterite deposit, is it more controlled by geochemistry or physical or lithological? That's my question. Thank you.
All right. Do you get it?
Yep. Thank you very much.
All right, sure.
Yes, very good question. Regarding the metallurgical constraints, yes, and that's true. I did not really mention this, but it's possible also to take into account that's an approach that's possible to actually take into account metallurgical, and to do like more geometallurgical domains. So take into account metallurgical constraints to define domains. I think this is a very interesting approach, I think. Regarding the what is the most important between geochemistry or lithological in terms of domaining, it's really I would say both anyway. the easy one, but because it's also linked, in fact, because we know that by the genesis or the formation of the regolith profile is responsible for the geochemical variations. So when you go from the saprolite to the limonite, we know we go from a phase of constant volume to a phase of volume reduction with residual enrichments combined with the leaching of major elements like silica and magnesium, and residual enrichments in iron, chromium, aluminium. So it's very closely linked. So we cannot really separate this. It's an integrated approach. That's why when we do the domaining, the vertical, like the first approach as a stratigraphic domaining, we cannot. What I want to say is that only using one aspect is taking a risk to miss something. So we should use as many information as we can to define the best domains. So you could actually work with only chemistry because you know you should probably not be very wrong because you know what is the behavior of the geochemical elements. So you could use geochemistry only to define your domains. But why not looking at geology? Because it will help you to actually define, to refine your domaining. And this goes both ways. So when you're asking what is the most important, it's hard to reply. It's like both information are important, and because they are here, they are available, so you need to use them. That's what I would like to say. If that makes sense. Yeah. Yes, that's what I wanted to say basically. But yes, a good point for the methodology. I think it's you can actually could combine some geological criteria and do some geology. Actually, I can add something that in New Caledonia there is a company. What they are doing, their sampling is already kind of geometallurgical in the sense that there is a ore processing process, a screening process, which is taken into account in the logging and sampling. So let's say there is a screening, let's say a 10 centimeter screen size. So this size is taken into account in the actual logging and sampling because we know that this is the screening size. So somehow we integrate some geometallurgical parameters in the process, in the geological process, as an example.
All right. Thank you.
Thank you very much. Interesting discussion. Thank you, Guillaume.
All right. We still have the last question. Who's the raised hand, the last ones? And you can, okay, Aditya, come on. You can go with your question.
Okay, thank you very much. Hello, Mr. Guillaume. I'm the last moderator in the last season, yeah, part 1. Hello, my name is Aditya. I'm from Zhejiang Cobalt, and I would like to ask about, we're back to the geophysical instrument, yeah. I would like to ask about how does the GPR or ERT help us to identify the subsurface or geological domain, yeah. We continue to the last one. To identify geological domain or like a limonite, saprolite, and how reliable is that? Instead we narrowing the grids, or could we just combine from the 25 spacing grid using the and combine with the geophysical interpretation?
Oh, okay. So for the GPR, so in my experience, okay, GPR is being used quite a lot, I think, in Indonesia by a number of companies. I think a lot less in New Caledonia, in my experience. My understanding is that GPR works quite well to define the limonite thickness. Not always very well for the saprolite, mainly due to the fact that there is a very high moisture content in the saprolite, and it's not really very accurate. So in terms of how reliable it is, so I would say in my experience, it's quite reliable, but this is based on only one deposit. Quite good reliability overall for limonite, and less in saprolite. But I guess for each deposit is going to be different. From what I know, I have experience of ERT in New Caledonia, so which is a bit more appropriate to define the bedrock boundary. And I know a study, for example, where someone compared the application of ERT in one deposit, and they found that it was working really well.
Tidak langsung beres yang desain.
Yeah, it was working very well, comparing, of course, with drilling, looking at drill holes and comparing the interpretation, and it was working quite well. But in a different deposit, both deposits were plateau-style deposits. One was a continuous plateau, and one was dissected, but I don't think it makes a big difference in this case. But the other deposit, it's like the interpretation was wrong, or more than 50% in the case was quite really wrong, and we could really not predict anything. And it was the conclusion of the study was a bit it was difficult because it was not very clear what were the factors explaining why in one case it works quite well, in one case it worked less. Because in both cases, I think the nature of the water was similar. So it's what I wanted to say here is that until we have number of drill holes to validate in different areas, so if you have a big deposit, I think the key is to do a few survey lines as a test in different areas, have a number of drill holes on these lines, so that you can kind of assess the applicability of the method for a given deposit. I think this is the best approach because you can do all the assumptions depending on the type of rocks and the water content and many things. Until you try, it's sometimes the best way is to do that. But if it works, it can really it can be very powerful because you can not only help the actual creation of the domains, but it can also help for the resource classification, as I mentioned. It can help for drill planning or optimizing the drill spacing. So it can be really powerful, and it's obviously less costly, especially GPR, than drilling. So I think it's always worth to invest in this approach, looking at this information. Yes, I'm not sure. Did I reply to the question fully, or did I miss something?
No. Yeah, about what I see in the ICP 2018, 18 ya. Could the ERT or HPR identify the structure and how it influence the laterite profile?
Yeah, that's an example that which worked quite well. Obviously, that's why it's here, and it was published in a PhD study, actually, PhD work. And you can see on the sections, of course, it's an interpretation, but the signal is here, the resistivity signal, and you kind of guess, pretty much see these structures here. Of course, yeah. So yeah, it's a good way, and ERT can be a good way to identify structuration, so it can really help a lot. To help define the structures and maybe help domain, define geographical domains. For example, here it's very clear that you have some structure controlling some weathering cells, but we are here more in this case, we are more in very much slope style. environment. So that's why we have this small weathering with volumes controlled by structures. Yes, but this is a case which works quite well. But I've seen also cases where the same profile doesn't work. And so that's why. And I'm just saying we have to be careful because as often in geophysics, using geophysics is a great tool, but until we have some drill holes, I would never put my hands in the fire for based on geophysical results.
Okay, thank you.
The last question from Adit is the last of our event today, and thank you very much for the participants to attend this this webinar, and also thanks you very much, merci beaucoup for you, Guillaume. It's very excellent presentation today. We understand a lot about the resource estimation, particular in the nickel laterite subjects. Thank you very much. And now, because this is the end of our event today, I will transfer to the secretariat. There is a one or two what you can share here for us before we close this webinar today, right? Anyone from secretariat will give salutation or whatever in this seminar?
Mau reminder aja untuk seluruh peserta, Pak. Bagi yang belum mendaftar sebagai member Mgei bisa mendaftar menjadi member IAG terlebih dahulu, lalu menjadi member Mgei sekarang bisa juga dilakukan melalui websitenya Mgei. Sebentar saya izin share screen, Pak. Saya stop dulu share-nya Pak Guillaume. Stop. Apakah sudah terlihat?
Belum. Oke.
Ya.
Alright.
Jadi bagi yang ingin mendaftar menjadi member Mgei bisa melakukan pendaftaran terlebih dahulu menjadi member IAG di website IAG di www.iag.or.id. Jika sudah melengkapi form pendaftaran, bisa melanjutkan mendaftar menjadi member Mgei. Di mana kalau sudah menjadi member dari Mgei bisa mendapatkan informasi update mengenai webinar-webinar atau diskon-diskon untuk mengikuti workshop-workshop sekitar geologi ekonomi. Kurang lebih seperti itu. Sekian dari sekretariat Pak Feryadi.
Untuk ngambil foto ada nggak?
Gimana Pak?
Close the event untuk pengambilan picture.
Oh ya, boleh Pak. Nanti saya bantu capture dari sini.
Alright, oke. Kalau sudah beres, sudah ya. Oke, anyway, thank you very much, Mr. Guillaume. Hope see you again sometime. Merci beaucoup.
Merci.
Au revoir.
Terima kasih.
You're very welcome. All right. So thank you very much for all participants to attend this seminar. Great. Hope we see you again next time and have a good day.
Oke, thank you, Pak.
Thank you, Pak.
Thank
Terima
you.
kasih, merci
Thank you.
beaucoup.
Sampai jumpa lagi.
Guillaume.
Thank you.
Thank you, Pak Bill. Good luck.